You know that force that keeps your feet planted firmly on the ground and the one that keeps the Earth from flying off into space? Well, for almost all of human history, nobody had a clue they were the exact same thing. Today, we're going to dive into the incredible story of gravitation. Okay, so let's start with two things we can all see. You've got an apple falling from a tree, right? It goes straight down. Simple. Then you look up at the night sky and you see the moon just circling us. It's not falling down, but it's not flying away either. It seems like these two things have absolutely nothing to do with each other, like they're playing by totally different rules. But what if they weren't? What if a single invisible force was pulling the strings on both the apple and the moon? That's the question one of the most brilliant minds in history asked. And let me tell you, the answer he found didn't just change science, it changed everything.
So to really get this, we've got to jump in our time machine and go way back. Back to a time when scientists were wrestling with two giant puzzles that seemed completely unrelated. One was right here on Earth, and the other was way out there, in the heavens.
Okay, so the earthly puzzle, it's pretty straightforward. Why do things fall down? And the big cosmic puzzle was, how in the world do the planets move? I mean, they just wander across the sky. For centuries, people just assumed these were two separate worlds with two totally different sets of rules. What happens up there stays up there. But slowly, bit by bit, that cosmic puzzle started to crack. You had brilliant thinkers from Aryabhata in ancient India to Copernicus in Europe who started questioning if Earth was really the center of everything. But the real hero of this part of this story, the guy who did the grunt work, was Tycho Brahe. This man spent his entire life just watching the sky, meticulously mapping and recording where every planet was night after night. He didn't know it, but he was building the exact key needed to unlock the whole mystery. And who gets that key? Well, it was Tycho's own assistant, a guy named Johannes Kepler. He inherited this absolute mountain of data, and he dove in. Kepler was the one who finally figured out how the planets actually move. Now, he couldn't tell you why they moved that way, but he could describe it perfectly with three incredibly elegant laws. Okay, law number one, the law of orbits. For thousands of years, everyone, and I mean everyone, just assumed the planets moved in perfect circles. It seemed pure, divine. Kepler proved them all wrong. He showed they actually move in ellipses, kind of like squashed circles or ovals. And the sun isn't even in the middle. It's off to the side, at one of 2 points called foci. The idea that the heavens weren't perfect? Whoa. That was a huge revolutionary deal. Then comes his second law, the law of areas. Now, this one sounds a bit technical, but what it really means is something amazing about how fast the planets are moving. It means a planet actually speeds up when its orbit takes it closer to the sun, and then it slows right down as it gets farther away. So their speed isn't constant at all. It's always changing in this predictable rhythm. And his third law, the law of periods. Okay, this one's got some math behind it, but don't worry about that. The big takeaway is this. It creates a perfect mathematical link between how long a planet's year is and how far away it is from the sun. It's a simple, beautiful rule. The farther out you go, the longer your trip around the sun takes. Period. And you can see it right here. Look at Mars. It's farther away from the sun than we are, and just like the law predicts, its year is almost twice as long as an Earth year. It's perfect. So Kepler had cracked the code. He gave us the how. He laid out the rules of the cosmic game. But the biggest question of all, the why, well, that was still a total mystery. Until a guy named Isaac Newton came along. He's the hero of our story. He's the one who finally connected the dots, who looked at that apple falling and the moon orbiting, and came up with a single universal why that explained not just those two things, but, well, everything. This was it. This was the light bulb moment that changed the world. Newton realized there aren't two sets of rules for the universe. The physics down here on Earth is the exact same physics up there in the heavens. That pull bringing the apple to the ground, it's the same force that's constantly tugging on the moon, keeping it in its orbit. It's all the same thing. And he gave it a name, gravity. And this idea became his universal law of gravitation. Get this. It says that every single thing with mass in the entire universe is pulling on every other thing with mass. Right now, you are pulling on me, you're pulling on the planet, you're even pulling on the sun, just the tiny bit. We're all locked in this giant cosmic dance. And the rules are simple. The more stuff something is made of, the more mass, the stronger its pull. And the further away you get, the weaker that pull becomes.
And he boiled this entire cosmic dance down into one simple, beautiful equation. Now, you don't have to be a mathematician. Just look at the r squared on the bottom. That's the distance. That squared part is so important. It means the force gets weak fast. If you double your distance from something, its gravitational pull on you isn't half as strong. It's 4 times weaker. Triple the distance, and it's 9 times weaker. That's why the sun keeps us in orbit, but a star a billion times bigger, way far away, doesn't even budge us.
Okay, so a universal law is great, but what does it actually mean for us, living our lives here on Earth? Let's check out some of the coolest and weirdest consequences of this. First up, we got to talk about something called free fall. Now, this isn't just jumping out of a plane. In physics, free fall is a perfect, idealized situation where gravity is the only thing acting on an object. Imagine a place with no air, a vacuum. Because it's in this perfect vacuum that gravity shows us what it's really all about. So that brings us to the classic riddle, right? If you're in a total vacuum and you drop a heavy hammer and a light little feather at the same time, which one lands first? I mean, everything we've ever seen in our lives tells us the hammer hits the ground while the feather is still floating around. Easy peasy. Yeah, but it's wrong. In a vacuum, they hit the ground at the exact same instant. It's mind-blowing, but it's true. And the reason why is one of the most fundamental rules of our universe. Gravity pulls on every object with the exact same acceleration. We call this acceleration g, and it doesn't matter if you're a feather or a bowling ball, g is the same for everything. So here's a fun one. Where do you think gravity is strongest? You might guess it's at the very center of the Earth, right? Makes sense. But nope. The pull of gravity is actually at its maximum right here on the surface. See, as you go up into the sky, you get farther from the Earth's center, so gravity gets weaker. But here's the wild part. As you go down, into a deep mine, for example, all the rock and dirt above you starts pulling you up, canceling out some of the pull from below. So the total pull gets weaker whether you go up or down from the surface. Weird, right? All right, so gravity does a pretty good job of keeping us stuck here. But what if we want to leave? What does it actually take to break free from Earth's pull and head out into space? Well, it takes one thing, a whole lot of speed. This magic number is called escape speed. Think of it like this. It's the minimum speed you need to be going at launch so that if you just shut off your rockets right away, you'd still have enough oomph to just coast away from Earth forever and never get pulled back. And for our planet Earth, that speed is absolutely insane. It's 11.2 kilometers per second. Let that sink in. That's almost 7 miles a second, or over 25,000 miles per hour. It's basically the universe's speed limit for leaving home. Now, let's compare that to the moon. Its escape speed is way lower, just 2.3 kilometers per second. And that makes perfect sense, right? The moon has a lot less mass, so its gravitational pull is much weaker. In fact, this is the exact reason the moon has no atmosphere. Any gas that might have been floating around would have been moving fast enough to easily hit that low escape speed and just drift away into space ages ago. Look, there's no doubt about it. Newton's law was a masterpiece. It explained apples, moons, planets, even galaxies. It worked everywhere. But it wasn't the complete story. At the most extreme places in the universe, places like the crushing center of a black hole, where gravity becomes unimaginably strong, well, that's where Newton's beautiful, simple laws start to fall apart. And that breakdown opens the door to an even crazier story, a story about bending space and time itself.